Okay, let's start. So today we are going to look at this particular question. How to construct a basis for real numbers as a Q vector space. And this particular question arose from our discussion yesterday about finding additive functions, non-trivial additive functions from reals to reals. Yeah, additive means which preserve addition. So here is first answer. Yeah, so we have to define, we have to construct a basis. Yeah, I mean I want to point your attention to this word, construct. Right? If we want to construct, then the first answer is use well ordering theorem. So what does well ordering theorem do? That every set is well ordered, every set can be well ordered. So let us say that less than is a symbol for a well order on real numbers. So that will give us a list. Yeah, well ordering means an isomorphism with an ordinal number, because every well order is isomorphic to a unique ordinal number. So therefore we'll get a well ordering, and that will give us a list of all the elements of real numbers. So what do we do now? We should define B0 equal to empty. Okay, so I'm going to use transfinite recursion to define a sequence of linearly independent subsets of RQ. RQ means reals as a Q vector space. Okay, so B0 I will define to be empty, and whenever and if B alpha is defined for alpha less than beta and B alpha is linearly independent, then define B beta equal to one of the two, B alpha if B alpha union x beta is not linearly independent and B alpha union x beta otherwise. Okay, so what am I doing? I am going to add. So let us look at what is happening at zeroth level. 0 is empty. Empty set is linearly independent. Yes. So what will be B1? Well, in order to define B1, I should know B0. So B0 I know, it is empty set. So now what do I do? Well, maybe I should change it slightly. This I should say singleton x0 if x0 is equal to 0 and otherwise. Sorry about that. So B0 is either empty or singleton x0 depending on whether x0 is 0 or not, because singleton 0 is not linearly independent. Yes. So now I know B0. How do I define B1? If B0 union x1, singleton x1 is linearly independent, then I will add it. If it is not linearly independent, I don't add it. And I do this for every number, for every ordinal, for beta less than gamma. Right, for every number I will do this. Whatever I obtain at the end, that thing will be my basis. However, yeah, there is something happening here which we don't quite understand and which contradicts the word in the double quotes. Right? How are we constructing this? Well, your answer could be that we are using transfinite recursion to construct it. But when can we apply transfinite recursion? After using well ordering theorem. But how does the well ordering theorem construct a well ordering in the first place? Huh? Axiom of choice is equivalent to well ordering theorem, yes, but how does even axiom of choice construct a choice function? The answer is we don't know. It is just an existential statement. It doesn't really tell us how it obtained. It's magic, essentially. Right? It doesn't know how to obtain that well ordering. It just says that, okay, I can do it. So therefore, the word construct is quite controversial here. Yeah, this is not a constructive approach to doing something. By magic, we are obtaining a well ordering. Now, I am going to give you an answer too. And before that, I will tell you what is Zorn's lemma. Okay, so if P less equal is a non-empty poset, please stop me if you don't understand any of the words. Non-empty you understand, poset you understand, such that every chain in P less equal has an upper bound. Then P less equal has a maximal element. Okay, let us try to understand what it's saying. Yeah, this is very complicated to understand at the first go. Yeah, every chain has an upper bound. So, if I know how to go up and up and up, then I always know how to go even higher than that. Then there is something where going higher process must stop, which means it's a maximal element. Maximal means there is nothing strictly above it. Once again, please try to understand that this is an existential magical statement. Whatever property you assume that, yeah, you can go up and up, every chain has an upper bound, but how does it obtain that maximal element? No answer. It's magic. Yeah, because this is not a constructive way of obtaining this maximal element. So normally, there are two things important about Zorn's lemma. First thing is, what is it trying to say? And second thing is how to use it. In mathematics, this particular statement is very commonly used. Yeah, because it has some desirable consequences. But how to use it? So, I am going to read a quote from William Timothy Gowers. So, Tim Gowers is a Fields medalist. Okay. So, when internet was just starting, then he started writing a blog. And I welcome you to check his blog on Zorn's lemma also. Yeah, Tim Gowers. I will give you a name. Yeah, Tim Gowers, British person. I have met him in person as well. So Tim Gowers on Zorn's lemma. This is a weblog. Okay, so what does he say? How to use Zorn's lemma? Yeah, I will read the quote. If you are building a mathematical object in stages and find that, first condition, you have not finished even after infinitely many steps. You have not finished even after infinitely many steps, and there seems to be nothing to stop you continuing to build. Yeah, there seems to be nothing to stop you continuing to build. Then Zorn's lemma may well be able to help you. Okay, so therefore, I mean this quote is quite famous about Zorn's lemma. So please do read Tim Gowers' weblog on Zorn's lemma, and even other articles. Yeah, he writes really nice expository articles. So now let us try to use it. So in general now, yeah, I mean see, we want to construct a basis of real numbers, and for that purpose what do we need? A poset. Where is this poset coming from? What do we want to construct? A basis. What is a basis? Can you define a basis? It is a maximal linearly independent set. Okay, maximal, that word is important. So that word is also present here. So therefore now we want to have a go at a complete attempt at finding a maximal linearly independent set. So what will our poset consist of? The partial attempts. If we want to construct a complete attempt, we should know the entire collection of partial attempts. Now what are partial attempts? Just linearly independent subsets. So that will be our poset. So to construct, so let P be the set of all linearly independent subsets of R over Q. Okay, then P subset is a poset. Correct? P subset is a poset because one linearly independent set contained inside another linearly independent set, that's a partial order relation. That much we know. Okay, is it non-empty? Tell me, is it non-empty? Does there exist a linearly independent set? Which one? Any singleton? Okay, so clearly non-empty, since singleton 1 belongs to P, we have P is non-empty. Okay, now let S be a chain in P containment. So what do we need to prove? That it must have an upper bound. So what is S? S is simply a collection. Yeah, let S be, I am just going to call it AI, I in I. Okay, this is a collection. So this collection is a chain. What does that mean? That any two AIs are comparable, means either AI is a subset of AJ or AJ is a subset of AI. One of them happens. Okay, so now can you tell me how to construct this upper bound for S? What is an upper bound? Which means it should contain all the AIs. How to construct something like that? Union, yeah? There is only one obvious choice. So let C be union of S, which is also union of AI, I in I. So what do we need to claim? Claim that, oh sorry, before I claim something. So clearly AI is a subset of C for each I in I. So therefore it is an upper bound. In the power set of real numbers it is an upper bound, but it will be an upper bound in P only if and only if C is also linearly independent. So we need to show, so we claim that C is Li, linearly independent over Q. Yeah, in this case linearly independent over Q, and please be aware that the same proof will give you a basis for every non-zero vector space. Yeah, I am doing it for reals over rationals, but every vector space has every non-zero vector space has a basis. The same proof will work because I am never using any particular properties of reals or rationals. Okay, so why is C linearly independent? How do you check whether C is linearly independent or not? We have to start with a finite linear combination which is 0. So let summation Ci xi I running from 1 to n be 0, where xi's are coming from C and ci's are rational numbers. Okay, so let me draw some diagram here. Yeah, I mean here I have AI1, here I have AIJ, here I have AIK, whatever, I have a chain over here, and my C is sitting here. Okay, now when I say that xi is in C, what does that mean? Oh, I'm making a mistake, sorry. I should write J because I have already used I, so please change this to J. I have used I for elements of S, right. So xj is in C. What does that mean? What is C? So where is xj coming from? Very good. So since C is equal to union of AI, I in I, each xj belongs to some Aij in S. Okay, but how many are there here? How many such Aij's are there? N many, means finitely many. So now there is only a finite number. So let's say that this and this and this. So these are the only 4 Aij's which contain these Xij's. Now when I have only finitely many, then the maximum amongst them must exist. They are all comparable, and when I compare only finitely many things, there is a unique maximum. Okay, so let AI0 in S be such that xj belongs to AI0 for all j equal to 1 to up to n. I will find some maximum, and moreover this maximum also lies in S because it is one of them. It is some Aij, right? So therefore I found this. Now here what can I conclude? So basically now I have a linear combination summation Cj xj which is a finite linear combination of elements of AI0. So therefore, because AI0 is linearly independent, I conclude that CIs are 0, CJs are 0. So since AI0 is linearly independent, we conclude that little Cj is equal to 0 for all j equal to 1 to up to n. Okay, so what did we show? We started with an arbitrary linear combination and we showed that, well, it must be a trivial 0 linear combination. So therefore, I have proved the claim. C is linearly independent. Okay, any questions so far?
That we have proved only for net finite, like j is equal to 1 to n, not for net infinite case.
No, but we never consider infinite size linear combinations. Yeah, we don't want to deal with conversions. In vector spaces, every element is a finite linear combination of basis elements, right? So linear independence only has to do with finite linear combinations, nothing more, nothing less. Any other questions? Okay.
So why you have taken that each of the x's belong to the same AI0?
Oh, because they are comparable. So see, AI1, Aij, and so they are all lying on a chain. So therefore, there must exist a largest one of them. So that is my AI0.
And also, so that there you used s equals to ai where I belongs to capital N, means that s it can also be finite.
S can be finite, yes. It can be finite, it can be infinite, it's anything arbitrary. Yeah, just because any two AIs are comparable means one of them is a subset of another. So therefore, now when you take union of finitely many sets, it is one of them. Yeah, where any two are comparable, it is one of them. Yeah, that's all I am using. Okay, so my proof of claim is done. So I can use Zorn's lemma and magic. Yeah, so by Zorn's lemma, P containment has a maximal element, say B for a basis. Yeah, let this be a maximal element. It is a maximal element. Yeah, I am never claiming maximum. Maximal element, say B. Then we need to check that B is a basis for RQ. What is basis? So B is linearly independent since B belongs to P. So it is linearly independent. And what is the other thing we need to check? That it spans. Okay, very good. So now B spans RQ. Suppose not. Then there exists some Y in R which is not in span of B. What do I conclude from here?
B is not maximum.
Then B union singleton Y is linearly independent and B union singleton Y is proper superset of B, contradicting maximality. So therefore, this cannot happen. Yeah, so this contradiction proves that B spans RQ. And I am done. I have found the basis, but there was some magic involved. Yeah, Zorn's lemma is magic. Any problem? Any question? Okay, so now perhaps some of you have asked me what is the actual statement of axiom of choice. I thought I already told you, but let me write it. So axiom of choice. Suppose I is a non-empty set and xi, I in I, is a family. Family means just a set, okay, nothing more. It's just a way of saying things. A family of non-empty sets. Then there exists a choice function C from I to union of xi's, I in I, satisfying C of little I belonging to xi for all I in I. Yeah, this is simply the definition of a choice function. So, there exists, right? We don't know how to construct it. Axiom of choice just guarantees that there exists. There is a way, so yeah, I mean, I'm just going to state in this class that axiom of choice, well ordering theorem and Zorn's lemma, these are equivalent statements. I'm not going to prove it. The proofs are long and I don't think for your level those are suitable. Hopefully you can get a feel that all of them are existential statements. So therefore they should be equivalent. Yeah, Zorn's lemma guarantees under certain hypothesis, it guarantees existence of a maximal element. Axiom of choice guarantees the existence of a choice function and well ordering theorem guarantees the existence of a well ordering. But historically, I mean, all of these statements, I mean, Zorn's lemma is called Zorn's lemma because Zorn gave a proof. He used axiom of choice, of course. Yeah, he gave a proof of Zorn's lemma. Well ordering theorem is called a theorem. Yeah, it's not really a theorem. It doesn't follow from other things unless you assume axiom of choice. So basically the status, yeah, I mean Zorn's lemma, axiom of choice and well ordering theorem, they are equivalent. What does that mean? It means that if I assume Zermelo-Fraenkel set theory's other axioms and then I assume axiom of choice, then I can prove ZF plus well ordering theorem. Then from here I can prove ZF plus Zorn's lemma, and from there I can prove ZF plus AC. Yeah, this is what we mean by them being equivalent. However, historically these three statements have had very different backgrounds. Yeah, axiom of choice. Yeah, I mean when you say I want to select one element from xi where xi is non-empty, then yes, obviously you should be able to do it. Then well ordering of real numbers, yeah, that face lot of opposition. Real numbers cannot be well ordered. Yeah, I mean there is continuum many of real numbers. You cannot have that. And Zorn's lemma statement has this condition that it should be a non-empty poset such that every chain has an upper bound. Now that is too complicated to understand. Okay, So therefore there is a quote. Yeah, I'm just going to write that quote. This is a joke. Yeah. Jerry Bona is a mathematician, American mathematician. He made this joke. So axiom of choice is obviously true. Well ordering theorem is obviously false. And Zorn's lemma, who knows? Yeah, this is only a joke. I have seen students writing it in exam. Yeah, please don't do that. It's just a joke. Yeah, obviously all those three statements are equivalent. But because of their perception amongst mathematical community, this is a true statement also. Yeah, as I explained, axiom of choice looks obviously true. Well ordering theorem looks obviously false, and Zorn's lemma is too complicated to comprehend. Okay, so now a little bit about the philosophy of this main theorem. Yeah, because main thing, axiom of choice. So historically this all began when Bertrand Russell, we have already mentioned his name, Russell's paradox. Yeah, so Bertrand Russell posed this very interesting question. So everybody wears footwear, yeah, some or other kind. So now if there are infinitely many pairs of shoes, let's say countably infinitely many pairs of shoes, then can you choose one shoe from each pair? Yes? How will you do it? Yeah. Okay. So you are saying that always choose the left one from that pair. Okay, for each pair you choose the left one. Now this gives us a choice function. What is xi? Xi is a pair of shoes, and out of them it is non-empty because it contains two elements precisely, and I can choose the left one. Now the next question is, what if I replace pair of shoes by a new pair of socks? Have you ever been confused when you buy a new pair of socks, then which one to put in which foot? Yeah, because they look identical. Now you answer the same question. With a new pair of socks, how do you choose one sock from each pair?
So cannot we arbitrarily choose any?
What is the meaning of arbitrary choice? Please explain.
Take any one of them.
Take any one, but you had to make that any one choice for each one. Can you do that?
Take the one which is kept on the left side.
Exactly. Okay, that was the kind of answer. Yeah, if we know the location of those socks in the physical space, then I have some extra data. Yeah, I can write down that this is the sock on the left side, this is the sock on the right hand side. But a priori, if I do not give you that data, then how will you do it? I don't know anything about those two elements in xi, and I still have to make a choice. So the answer is we cannot determine this. If we know their positions in the physical space, then obviously, yeah, this is the one kept on left. But if we don't know anything extra about it, then we have no way of figuring out how to choose one from each pair. This is very similar to real life. In real life, all of you are sitting here right now. Are you all here by your choice?
Yes, there's no attendance.
There's no attendance, so you are here by your choice. but some people are just afraid to pass, like to fail, and therefore they are sitting in this class. Some people just want to learn more, therefore they are sitting in this class. Some people just were grabbed by their friends, okay, I'm going, why don't you come with me? Yeah, so there are different reasons, so I cannot call everything a choice. Right, so some people are here because of some other reasons. Yeah, they don't really want to be here, they would rather go and sleep. So basically in our life also we make lot of choices. Yeah, some people say that your choices define your personality, your choices define your identity. But do we make only finitely many choices, or we make infinitely many choices? Well, it's a rhetorical question. I don't know the answer, you don't know the answer, nobody knows the answer. So, even if we agree that we do make infinitely many choices, we cannot prove it. And if we say that we cannot make infinitely many choices, then also we cannot prove it. And similar is the status of axiom of choice in maths. Axiom of choice cannot be proved, and negation of axiom of choice also cannot be proved. So, negation of axiom of choice means that there exists a family of non-empty sets, an infinite family of non-empty sets, from which we cannot choose one element. Like there doesn't exist a choice function for that. We cannot produce such a family.
If I is finite.
Yes, I am coming to that. If I is finite, then we can obviously make choices. Because we'll have enough time, 1 million choices. We are given 1 million pairs of socks, new socks. New socks is important because once you wear them, then they will have a thumbprint. So then you can easily distinguish between them, left and right. Okay, but with new pairs, if you have enough time, then for 1 million pairs you can choose. This one, this one, this one, this one, this one. But infinitely many, yes. So that's the point also, that axiom of choice, when do we need it? And when do we not need it?
I is not finite.
If I is not finite, then also we don't always need it. So for example, I am telling you that xi is a collection of ordinals. Now this is extra information. Xi is a collection of non-zero ordinals. Then can I choose one element from each ordinal? The least one. Yes, I always know that 0, 0, 0, 0, 0 is a choice function. So therefore, if I know something extra about the sets in that family, then perhaps I can make a choice. If I know that xi is the collection of natural numbers for each I, whatever the size of capital I, then can I make a choice? I can always say choose one. Choose one for each of them. I mean C of little I will be 1. A constant function would do the job. So what do I know? If all the xi's are equal, then I know that extra information about xi's. If I have extra information, I don't need to use axiom of choice. Many times it feels like using axiom of choice makes our life easier. So that's why people tend to use it, but lot of effort is currently going in a branch of mathematics called constructive mathematics. So constructive mathematics means you construct everything that you use. So the first thing they reject is axiom of choice, because it's magic. So instead they will try to come up with new proofs of the same old theorems if possible, so that they can avoid axiom of choice. Without axiom of choice, imagine what happens. So we have two sets A and B. Do you know whether given two sets there is an injective function from A to B or an injective function from B to A. You know there is a function. If both of them are non-empty, then you always know there is a function, namely the constant function. But a constant function is not injective. So my question is, does there exist an injective function between any two given sets? I am not talking about CSB theorem here. Yeah, please be aware. I am just asking you whether there exists an injective function. Because existence of injective function means what? Like if there is a function, injective function from A to B, then cardinality of A is less equal cardinality of B. So I am asking you, can you compare cardinalities of any two sets? And the answer is we don't know. How do you construct an injective function? If you assume axiom of choice, which means equivalently well ordering theorem, then every set can be well ordered. So you can assign to it its cardinality, and any two cardinal numbers being ordinal numbers are comparable. So now you know how to find an injective function. First take a bijection with cardinal number which is an ordinal number, then that can be embedded inside the larger ordinal number and which is in bijection with the other set. Now this is a way of constructing an injection. But without using well ordering theorem, you don't have any way of constructing an injective function between any two given sets. So the cardinalities which should be the bijection equivalence classes of sets, they are not really properly defined. I mean, they are defined, bijection equivalence classes are defined, but they are not comparable. Initial ordinals do not really cover all cardinalities. You understand? So without using axiom of choice, even we cannot compare cardinalities of any two sets. So you would say that, yeah, this is desirable property. We should use axiom of choice. However, now there is also a downside to this. Yeah, axiom of choice has some undesirable consequences also. It gave us a basis of every vector space, yeah, so that is a desirable consequence, but it also has undesirable consequence. Now how? So given any finite length interval, yeah, any finite interval in real numbers, you can associate to it its length. Given a geometric picture in the plane, you can associate to it its area. In any regularly defined shape in 3 dimensions, you can associate to it, very good, volume. Now this area, length and volume, these all measure those sets. However, now when you are measuring, when you want to measure every single subset, like including something like Cantor set, okay, when you want to measure every subset of real numbers or every subset of R square or every subset of R cube, then you would like to have some properties, yeah. And first property is that, okay, if I have this set and they are disjoint, then what should be the measure of their union? The sum. Yeah, and you can expect the same thing to happen for infinitely many like families of countably infinite families of disjoint sets. You can expect that to happen, yeah, that the major function would be countably additive, because we have notion of convergence, so we can define sum of countably infinitely many numbers. Then you would also expect that, okay, if I have an interval here and I translate that interval to some other place, then translation doesn't really change my area, volume. Yeah, I'm just changing the location in the space. That doesn't change its inherent property, which is its measure. And if I have empty set, then empty set's measure should be 0. Okay. If I know these 3 properties, then can I measure every single subset of R square or R cube or R? The answer is no. Because axiom of choice provides you with a non-measurable set. Like you can mathematically prove that it is not measurable. What happens there is that you start with one sphere. One sphere, you understand? Sphere is like simply the ball, yeah, not the interior of the ball, just the surface of a ball. Now you break this sphere into 5 pieces whose existence is guaranteed by axiom of choice. Yeah, those 5 pieces, their existence is guaranteed by axiom of choice, and then you simply translate them and rotate them. Translation and rotation doesn't really change their volume, right? So you translate and rotate them and then you reassemble them. They will actually give you 2 spheres. One sphere broken into, I think it's actually a sphere. Yeah, I want to define a volume. So it's a sphere, interiors included. So this is called Banach-Tarski paradox. It breaks one sphere into finitely many pieces, which when translated and rotated, they reassemble to give you 2 different spheres. So magically, I mean, what happened here? 1 is equal to 1 plus 1. Our math fails here. So therefore, what people assume that, okay, there are non-measurable sets, then I always talk about a major space, or in probability course you might have learnt about sigma algebras, right? So those sigma algebras come from this perspective, that we cannot measure every single subset, we can only measure some subsets. So that existence of non-measurable sets is also a consequence of axiom of choice, which is an undesirable consequence. So it does something good, it does something bad. So basically the choice is up to mathematicians whether they want to use it or not. The choice about choice is up to mathematicians. So there are so many consequences. Yeah, in mathematics you will find many more desirable consequences of axiom of choice than undesirable consequences. So various like a large group of mathematicians tends to accept it as one of the axioms of Zermelo-Frankel set theory, and then they call it ZFC, Zermelo-Frankel choice, ZFC, because then lot of things become easier. Then because you can list elements of every single set. Yeah, you can always use well ordering theorem to list those things, and then you can use transfinite recursion, transfinite induction, so proofs become easier. But the problem with them is you don't know how you arrived at that position, because these statements are existential, they just magically guarantee existence of something. So every set, given any infinite set X, yeah, X cross X, is it in bijection with X? For every infinite set X, X cross X, is it in bijection with X? Now this is also an equivalent statement of axiom of choice. Okay, so there are many other so equivalents. For each infinite X, X cross X is in bijection with X. Then for each F from A to B, yeah, this we have already seen in the class. For each F from A to B, there is G from B to A, such that if I first do If I first do G and then do F, F composed with G is identity on B. So basically I can find the section. I can find the section of this function. Section means a way of, because for every little b in capital B I am choosing one element from its pre-image. So that pre-image F inverse of little b, that is xi in axiom of choice. Right, so this is also an equivalent statement of axiom of choice. To end this section, I would like to say that I have written a poem on axiom of choice. It's available on SoundCloud. If you are interested, please go and listen to that and figure out all the equivalents of axiom of choice. Okay, let's stop.